So in this problem, we have a chord, say on just like a guitar or something, and the tension is 170 newtons. We're told that the mass of this chord is 0.55 kilograms, and the distance between the connection points is 7.4 meters. We are asked to find, okay, what is the time it takes for a pulse? Let's say we pluck the string to reach from this end to that end, right? So we pluck a string, how long does it take to reach the other end? Okay, this can be found using the speed of a string formula is equal to the square root of tension over the square root of, and I forget what this is called specifically, but it's like a mass per unit length formula, and as you'll see, it's just mass over length. It's kind of like concentration, mass of something per unit volume. This is saying the mass over a unit of length. So linear mass density, I think is what it's called. You don't need to know it, but you need to know that it's a proportionality that spreads mass over a length of a string, for example. So we want to figure out what this is first, because if we can find what this is, we know what tension is. It's 170 newtons on the string. Then we could find the velocity, and to find time, we know that velocity is equal to delta x over delta t, and if we know delta x to be this, 7.4 meters, we'll find velocity, and therefore we'll find time. Sound like a good plan? Let's go for it. Okie dokie. So, linear mass density, let's figure it out. 0.55 kilograms, and you want to use Newtonian units, and the length here is 7.4 meters. Okay, so we found the linear mass density, which is mu, 7.4. This is going to be 0.0743, and I know that I'm using weird units here, but forgive me, Jesus. Kilograms per meter. Okay, we need to find the square root of that. So let's go ahead and take the square root of this number to give an approximation. Again, it's not exact. So I'll go ahead and say that the square root of mu, or the linear mass density, is 0.273. Okay, so let's just plug that in right here. And I'm not going to put units on it. And let's take the square root of the tension just to simplify our formula here. So the square root of 170 is approximately 13. And because I use 3 here, I know I can only use 2 sig figs. Just for the calculation's sake, I'll keep a couple decimal points. But when we take our final, we'll keep it to 2 sig figs. Okay, so we have 13.03 over that number there. So when we actually do this, we're going to get our velocity to be 13.03 divided by 0.273 is equal to 47.7 meters a second. So when we pluck the string, or like a chord, for example, it's going to that wave is going to travel at 47.7 meters a second. Okay. Remember what I said earlier? If we have velocity, we can just use the simple kinematics we learned at the very beginning of this course to find delta t. All right, so we know delta x is the 7.4 meters. That's how far we're moving. Right? We're going to bring the delta t to the top and divide by our velocity. So delta t is going to be equal to the distance we traveled over the velocity, right? That's going to cancel meters and give us seconds, right? If we have seconds in the denominator in a reciprocal form, well, that's going to bring it up to the top. Okay, so delta t, 7.4 divided by 47.7. We are going to see that the time it takes to go from one end of the string to the other is 1.55 seconds. So pretty short, fraction of a second there. That's going to be your answer there. I hope you enjoyed this episode. If you did, please drop a like, subscribe, comment if you have any questions on how I figured out this. Again, you should have been given that the formula of the velocity of a wave on a string is equal to delta not delta, square root of tension over square root of the mass, linear mass density. If you weren't given that, I'd put that on like a cheat sheet if you have it, or a formula sheet. It will help you out greatly. Hope you have a wonderful day.